41 trillion kilometers. Written out in full, that number would fill an entire line on this screen and still fall short of conveying the reality it represents, because it describes the smallest possible distance between us and any other star in the universe. The star closest to our Sun is called Proxima Centauri. It is part of the triple star system Alpha Centauri and lies exactly 4.24 light-years from here. Said like that, it almost sounds reasonable. It even sounds close when you remember that the observable universe spans 93 billion light-years in diameter. But that apparent closeness is an illusion, born from the cosmos's staggering scale. Understanding what those 4.24 light-years truly mean is one of the most unsettling and most fascinating mental exercises astronomy can offer anyone willing to stop and think about what they're seeing when they turn their eyes to the night sky. When you gaze up at night and find that point of light that is Proxima Centauri, the immediate feeling is of something distant yet perhaps reachable, like a lantern hanging high on a mountainside. The reality is something else entirely. What your eyes receive in that moment is a photon that left the star over 4 years ago. Not a live image, not a real-time transmission. Real. A portrait built from light that traveled 4 years and several months through the absolute vacuum of space before finally meeting your retina at this exact instant. The star you see is not the star as it exists now. It is the star as it was when you were 4 years younger than you are today. If Proxima Centauri vanished completely at this very moment, you would still see it burning in the sky. For 4 full years, with no way of knowing it, had disappeared forever. And that is only the distance expressed in light travel time. And light already travels faster than anything else in the universe. When you convert that distance into kilometers, the number shatters every perception you had about what it means to be far from something. A single light year equals roughly 9.46 trillion kilometers. The distance light travels in 1 full year, moving at 299,792 kilometers per second, a speed no known mass in the universe can even approach. Multiply that by 424, and you reach about 40.1 trillion kilometers. For a reference the human mind can grasp, the distance from Earth to the Sun is roughly 150 million kilometers. Proxima Centauri is 267,000 times that distance from us. 267,000 times the distance between you and the star that warms your face every morning. That comparison begins to warp perception in a useful way, but still doesn't fully capture reality. So try another scale, one that can be physically visualized. If you shrunk the Sun to the size of an orange and placed it on a table, Earth would be a grain of sand orbiting just over 10 meters away. At that scale, where an entire solar system fits inside a generous room, Proxima Centauri would be over 2,700 kilometers from that table, not 2,700 meters. Not 2,700 city blocks, 2,700 real kilometers, roughly the distance from Sao Paulo to Belém, crossing half a continent, and all the space between that orange on the table and that imagined star in Belém would be completely, absolutely empty. No floating rock, no visible dust, only the cold, silent, unimaginable vacuum of interstellar space, stretching in every direction, offering no stop, no waypoint, no reference. What this scale reveals is something most people never truly pause to absorb. The stars that dot our night sky are not close companions of Earth. They are neighbors separated by abysses of vacuum that defy all intuitive understanding. The starlit sky, which seems so full, so dense, so flooded with light, is, in reality, almost entirely empty space. Every bright point you see is a distant sun, some larger than ours, some smaller, some older than the solar system itself, all separated by voids that make the distances between cities, countries, and continents utterly insignificant by comparison. Proxima Centauri is the nearest of all in the known universe, and yet the distance separating us from it demands we completely redefine what the word far means. The scale of that void has concrete consequences reaching far beyond philosophy or poetry. It defines what is possible for a civilization that aspires to one day reach another star. It sets the limits of what physics allows and what engineering would need to overcome. And it begins to reveal a profound truth about our place in the cosmos. We are not isolated by a lack of stellar companions. We are isolated by the geometry of the universe itself, a geometry that built the space between stars with such a staggering generosity of vacuum that no human mind can visualize it without turning to metaphor. And the question this vacuum raises is not merely philosophical. It is the most practical question humanity can ask about its own future. What would it take to cross it? If humanity decided today to send a probe toward Proxima Centauri, what would be the first thing engineers would need to calculate? The maximum speed current technology allows. And that number, when it finally appears, completely transforms the conversation about what it means to be separated from another star by 4.24 light-years. The New Horizons probe, launched in January 2006 with the initial goal of studying Pluto and the outer reaches of the solar system, is one of the fastest objects humanity has ever placed in space. It travels at approximately 58,000 kilometers per hour. A speed that by any human scale is utterly extraordinary. At that speed, New Horizons would take roughly 73,000 years to reach Proxima Centauri. 73,000 years. When the first anatomically modern humans were leaving Africa and beginning to spread across the planet, that entire span of time would still need to pass before the probe reached the nearest star. To make this scale even more concrete, in 73,000 years, entire civilizations would have risen, flourished, and vanished dozens of times over. The Portuguese language you are hearing right now would no longer exist. No current language would survive in any recognizable form. The pyramids of Egypt are roughly 4,500 years old and are already considered relics of deep antiquity. The full journey to Proxima Centauri with our current technology would take the equivalent of more than 16 Egyptian civilizations stacked one upon another. And even after that astronomical wait, the probe would arrive with no humans aboard, no ability to return, and no way to transmit data back in any useful time, because radio signals also travel at the speed of light and would take another 4.24 years just to reach us. So what about Voyager 1? The most distant probe humanity has ever sent into space, launched in September 1977, and is still traveling. It moves at roughly 61,000 kilometers per hour, and after nearly 5 decades of uninterrupted flight, has covered more than 24 billion kilometers. A distance that sounds immense until you remember that Proxima Centauri is 40.1 trillion kilometers away. In other words, after nearly 50 years of continuous travel through space, Voyager 1 has covered less than 0.06% of the distance to the nearest star. At the same speed and heading, it would take tens of thousands of years to arrive. It will never get there, not on that trajectory, not with that technology. Humanity will exist in forms we cannot yet imagine before that probe ever crosses the full interstellar gulf toward our neighboring star. What these numbers reveal is not cause for despair, it is cause to truly grasp the real scale of the challenge. Physics is clear about what separates our current technology from what any practical journey to another star would demand. Even traveling at 10% the speed of light, a speed requiring energy equivalent to all of humanity's electricity consumption for several centuries, the journey to Proxima Centauri would take over 40 years of continuous travel. At 20% the speed of light, that time would drop to just over 20 years. But no existing technology can even remotely approach those speeds with any object of significant size. The barrier is not one of will or creativity, it is one of physics and energy. Light itself, the ultimate speed limit physics imposes on any object with mass, would still take exactly 4.24 years to cross that distance. This is not an engineering problem that more funding or incremental innovation can solve. It is a barrier written into the very fabric of the universe, one that makes every star you see not merely distant, but separated by a kind of distance that defies all human analogy. When you look at Proxima Centauri and imagine traveling there, you are contemplating a journey that would consume the entire recorded history of human civilization just to begin, using the means available today. That is the true weight of 4.24 light-years, measured not in kilometers, but in human time, in generations, in everything civilization built and lost, while those stars kept burning, indifferent in the sky. The distance is not a number. It is a statement about where we stand in the universe, and about how much of our creativity still must be unleashed before that statement can ever begin to change. That is precisely why what lies between here and there deserves to be understood with care, because crossing that space begins with truly grasping what it is. There is a question that almost never surfaces in conversations about interstellar distances, yet it completely transforms how you picture the space between us and Proxima Centauri. What exactly lies between here and there? Most people's instinctive answer is nothing. And that answer is wrong in a very interesting way. Interstellar space is not the absolute vacuum intuition imagines. It is permeated by something called the interstellar medium, an extraordinarily thin mixture of gas, dust, and charged particles that invisibly fills the entire galaxy. The density of this material is inconceivable on any human scale. On average, the interstellar medium holds roughly 1 hydrogen atom per cubic centimeter. A single cubic centimeter, the size of a small sugar cube, contains, on average, just 1 atom. Compare that to the air you breathe right now, which holds around 27 quintillion molecules in that same volume. Interstellar space is extraordinarily empty, yet that near void is far from inert. It is threaded by galactic magnetic fields stretching thousands of light-years in every direction. It is continuously bathed by cosmic rays, subatomic particles, accelerated to near-light speed by violent events like supernova explosions, neutron star collisions, and magnetic jets unleashed by supermassive black holes. These particles travel through the interstellar medium in all directions, including through the solar system, through Earth's atmosphere, and through your own body at this very moment. On average, dozens of cosmic particles pierce every square centimeter of your body every second, and you feel absolutely nothing. The space between here and Proxima Centauri is no inert tunnel waiting to be crossed. It is a dynamic, magnetized environment saturated with radiation, one that any interstellar vessel would have to endure across years or decades of continuous travel. There is also a precise physical boundary that defines where our solar system ends and true interstellar space begins. That boundary is called the heliopause. Beyond it, the solar wind, the constant stream of charged particles flowing from the sun in all directions, no longer has the strength to push back the particles of the interstellar medium. The heliopause lies approximately 120 astronomical units from the sun, roughly 18 billion kilometers. In August 2012, after nearly 35 years of uninterrupted travel, Voyager 1 crossed that boundary and became the first human-made object to enter true interstellar space. It was a scientific moment of extraordinary importance. For the first time in history, a human instrument was transmitting data from within the region between the stars, a region we had only ever studied from afar. The measurements confirmed that crossing the heliopause brought a clear shift in the magnetic field surrounding the probe and a sharp rise in cosmic particle density, proving the heliopause is a real, measurable physical boundary, not merely a theoretical line on astronomical maps. But even after crossing it, Voyager 1 remains almost incomprehensibly far from Proxima Centauri. The heliopause lies just 0.002 light-years from the Sun. Proxima Centauri is 4.24 light-years away. In other words, after crossing our solar system's boundary, following nearly 5 decades of travel, Voyager 1 has completed less than 0.05% of the journey to the nearest star. Interstellar space stretches far beyond what any probe ever launched has managed to explore. And what Voyager found at that boundary is only the beginning of what lies between here and there. Temperature in interstellar space varies in the most extreme ways. In what are known as cold molecular clouds, dense regions of gas and dust where new stars eventually form, temperatures can drop to just a few degrees above absolute zero, -273 degrees Celsius. In other regions, heated by intense stellar radiation or the remnants of stellar explosions, gas can reach temperatures of millions of degrees. Between here and Proxima Centauri, a hypothetical vessel would encounter these extremes throughout its journey, ranting, and would also face the relentless impact of interstellar dust grains. At velocities approaching a significant fraction of the speed of light, even a microscopic particle carries enough impact energy to destroy any material we know. The space between us and Proxima Centauri is not simply an empty distance. It is a physical environment with concrete properties that make the crossing an engineering challenge far greater than the distance alone suggests. Understanding what lies between here and there, the near-perfect vacuum, the galactic magnetic field, cosmic rays, the heliopause boundary, temperature extremes, and interstellar dust, is the first step toward taking seriously the idea of crossing that space. Because an interstellar journey is not simply a matter of traveling from one point to another in a straight line. It is a matter of surviving what exists between those points across a voyage lasting decades or centuries. And it is precisely because that space is this way, vast, dynamic, radiative, and almost incomprehensibly empty, that real proposals for crossing it are as fascinating as they are daunting. Despite everything thus about it, the impossible distance, travel times that exceed all of recorded human history, an interstellar environment that defeats any current technology, humanity has never stopped imagining how to cross that abyss. And the most astonishing thing is not simply that these ideas exist. It is that some of them are physically plausible within what physics has already established as possible. In 2016, an initiative called Breakthrough Starshot was publicly announced with a bold objective: to develop and launch nanoprobes toward Proxima Centauri within a few decades. The core idea is physically elegant in its conception. Tiny probes, the size of a computer chip, weighing only a few grams, would be equipped with ultra-thin, highly reflective sails. A high-powered laser built on Earth would fire a concentrated pulse of light against those sails. For a few minutes, the accumulated light pressure from that impulse would be enough, in theory, to accelerate the probes to roughly 20% the speed of light. 20% the speed of light. That number completely transforms the conversation about interstellar distances. At that speed, the nanoprobes would take approximately 20 to 21 years to reach Proxima Centauri, or to the journey entirely within the span of a single generation. 20 years of travel to the nearest star instead of 73,000. The difference is not one of degree, it is one of kind. But that number conceals a list of technical challenges that reveal exactly what it means to attempt something never before done in the history of engineering. The laser required to accelerate the sails would need to operate at tens to hundreds of gigawatts, an amount of energy demanding a technological infrastructure that does not yet exist anywhere on the planet. The sail itself would have to be built from a material that reflects light with near-perfect efficiency, while simultaneously withstanding the intense heat generated by the very laser driving its initial impulse. Over 20 years of travel, each nanoprobe would have to survive collisions with interstellar dust particles moving at a significant fraction of the speed of light. Impacts that, at such velocities, carry far greater energy than the particles' tiny size would suggest. Upon arriving at the Proxima Centauri system, the probes could not slow down. They would simply streak through the system at full speed, photographing and collecting data during the brief window of closest approach, then transmitting everything back to Earth. That transmission, traveling at the speed of light, would reach Earth another 4.24 years later. In total, from the laser's launch to receiving the first scientific data from Proxima Centauri, approximately 25 to 26 years would pass. A project starting today could deliver results within the lifetime of those now working on it. Why Proxima Centauri would be such a valuable destination has an answer that makes everything far more tangible. In 2016, analysis of astronomical data confirmed the existence of a planet orbiting Proxima Centauri, designated Proxima Centauri b. This planet has an estimated mass of at least 1.07 times that of Earth, completes one orbit every 11.2 Earth days, and lies within its star's habitable zone. That range of distances where surface temperatures could, under certain conditions, allow liquid water to exist. This planet is real. It is confirmed by observational data. It orbits the closest star to us in the entire universe. And though there is no confirmed atmosphere or water, and certainly no indication of life, its existence fundamentally changes the meaning of those 4.24 light-years separating us from Proxima Centauri by Ensotol, because now we know something concrete waits on the other side. Other approaches have been studied by physicists and engineers across the decades. Nuclear propulsion concepts, both fission and fusion, propose using nuclear reactions to generate thrust far beyond any existing chemical rocket. In theory, sufficiently advanced fusion engines could carry a spacecraft to several percent of light speed, compressing a journey of tens of thousands of years down to mere centuries. There is also the concept of generation ships, vast, self-sufficient vessels inhabited by multiple human generations across centuries of travel, with the descendants of the original crew arriving at the destination. This concept raises profound philosophical questions about what it means to send people on a journey from which they themselves will never return, trusting that their great-grandchildren will complete what they began. What all these projects share is that they reveal something fundamental about our species. Faced with an obstacle that seems insurmountable, the instinctive response is not resignation, but imagination. The distance to Proxima Centauri is real. The void is real. The laws of physics are real. And yet, engineers and physicists dedicate entire lives to seriously imagining how to cross that abyss. Not as science fiction, but as concrete pursuit. Perhaps what matters most is not whether these projects will succeed in the coming decades. It is what it says about us, that we keep trying to answer a question the universe posed when it created stars separated by trillions of kilometers of silent void. There is a specific moment when the distance between us and Proxima Centauri stops being just a number and becomes something you feel. That moment comes when you stop measuring it in kilometers or years of travel and begin measuring it in what it means for the concrete existence of every human being who ever lived on this earth. All the civilizations that rose on this planet, those who built Stonehenge, those who sailed the Pacific without modern instruments, those who raised the great medieval cathedrals, those who created writing systems more than 5,000 years ago. All of them looked toward that region of the sky, never knowing a star lay 4.24 light-years away, never knowing it had a planet, never knowing the star's name, its surface temperature, its mass, or the orbits of worlds around it. We know. We are the first generation in the entire history of life on this planet to hold that knowledge. And that is no small detail. It is a shift in our position within the universe. The light leaving Proxima Centauri at this very moment will take 4.24 years to reach Earth. When it arrives, some of it will touch your eyes or the eyes of whoever is alive in that moment and will seem like just another star in the dark sky. But you now know that light traveled 40.1 trillion kilometers to reach here, that it crossed a void where, on average, only a single hydrogen atom exists per cubic centimeter, that it passed the heliopause, entered interstellar space, crossed the dynamic emptiness between two star systems, and finally found your planet, your atmosphere, and your surface. Before reaching your eyes, that light is not merely light. It is a message about the scale of the universe, and every person who looks at the sky is its recipient, whether they know it or not. The isolation that distance creates is not empty or grim. It is an isolation that defines who we are and where we stand. We are a civilization on a rock, orbiting a mid-sized star, separated from the nearest star by an abyss our most advanced technology would take tens of thousands of years to cross. And yet, despite all of that, we keep looking up. We keep building larger telescopes, sending faster probes, proposing lasers to accelerate chip-sized spacecraft to 20% the speed of light, imagining nuclear propulsion, designing generation ships. No species that did not care about the cosmos would do this. No species purely focused on immediate survival would bother calculating the exact distance to a neighboring star and proposing concrete ways to cross it. We do this because something within us recognizes that this distance, though immense, is not infinite. What this distance also reveals is that the universe was not built to be comfortable. It was built to be vast, staggeringly vast, wonderfully unsettling. And the purpose of stars is not to serve as nearby destinations for a young species in a galaxy of 100 billion suns. The purpose of stars is to exist, to burn, to forge elements in their cores, to die in explosions of inconceivable energy, and to create dust that one day becomes new worlds and perhaps new forms of life. We are, in a sense, that chemistry and physics confirm with precision, made from the remains of stars that died before the sun existed. The iron atoms in your blood, the calcium in your bones, the oxygen you breathe right now, all were forged inside stars that exploded billions of years ago. The distance between us and Proxima Centauri is real, but the connection between us and the stars is older and more intimate than any distance can erase. When you step outside and look at the night sky, whether an hour from now or days from now, and see those points of light scattered across the darkness, remember that each one is separated from you by an abyss like the one you now understand, that the nearest star of all lies 40.1 trillion kilometers away, that the light you are seeing left years, decades, or centuries ago, that there is a confirmed planet orbiting that nearest star, and that you are part of a species that not only discovered all of this, but is beginning, slowly, ambitiously, and relentlessly, to imagine real ways of going there. The universe built this abyss between the stars. Humanity is still deciding what to do with it. And while that decision remains unmade, we are already doing the most important thing any conscious species can do, staring into the abyss and asking seriously and without surrender how to cross it. Do you believe humanity will one day cross that vast gulf and reach Proxima Centauri? And in which generation do you think it will happen? Leave your answer in the comments, because this is one of the most profound questions our species can ask about its future. If this documentary made the night sky look different to you, share it with someone who also deserves to feel the true scale of the universe. And if you haven't subscribed to this channel yet, do it now, because every video here is a journey to places few dare to truly explore.